Hi everyone, welcome to the first lecture of the ETI 4186, Introduction to Reliability Engineering. Before we dive into the definition and theory of reliability engineering, I want you to consider the sovereign reality. Things fail, right? When they fail, the consequences can be catastrophic. There are many examples mentioned in the textbook, and I would like to mention the two tragedies here. In 1940, Tacoma Narrows Bridge collapsed only after 5 months old. In 1986, Space Shuttle Challenger exploded in the air, resulting from the failure of its rubber O-rings. These tragedies could have been prevented with better reliability engineering, and we are going to explore why things fail and how we can predict and prevent failures, and why reliability engineering has become one of the most critical disciplines in the modern engineering fields. What is the objective of reliability engineering? So reliability and maintainability engineering attempt to study, characterize, measure, analyze the failure and the repair of the systems in order to improve upon their operational use by increasing their design life, eliminating or reducing the likelihood of failures, reducing safety risks, and reducing downtime. Traditionally, engineers use deterministic methods with large safety factors, but this approach often results in over-design, thus increasing costs, or sometimes under-design when unexpected load occurs. In contrast, the approach taken in reliability engineering treats failures as the random occurrences. It is a more realistic and practical approach because it acknowledges the inherent uncertainties and complexities of the real-world systems. In this slide, I'm going to give you 3 fundamental definitions that form the foundation of this field. The first one is reliability. Reliability is defined as the probability that a component or system performs a required function for a given time when used under stated operating conditions. We denote this as RT. The second one is maintainability. It's defined to be the probability that a failed component or system will be restored or repaired to a specified condition within a period of time when maintenance is performed according to a prescribed procedures, and we denote this as the MT. And the third term is availability, which is the probability that a component or a system is performing its required function at a given point in time when used under stated operating conditions. You might wonder why reliability engineering has become so important and why do we need to study this. There are several key driving forces. The first one is increased complexity and sophistication of systems. Modern systems are incredibly sophisticated. A simple smartphone contains more computing power than the computer that sent humans to the moon. As complexity increases, the number of potential failure modes grow exponentially. Let me show you this example. If we have components each with 99% reliability, we need just 2 of them to work together, your system reliability dropped to 98. With 10 components, it's down to 90%. But with 50%, you're looking at only 60% reliability. So in other words, complexity is the enemy of reliability. The second driving force is the public awareness and quality demands. Consumers are more informed and demanding. According to the Gallup survey, it showed that lasts a long time score 9 out of 10 in importance to our consumers. And the fourth place is the easily repaired. Those two factors are the important factors to our customers. The third driving force is the government regulations. We now have extensive regulations such as the Food Drug Act, National Traffic and Motor Vehicle Safety Act, and etc. Those laws and regulations represent our society's demand for safe and reliable products. Driving force is the economic considerations. The cost of failure, repairs, and warranty for many products can be enormous. It is much cheaper to build a reliable product from the very beginning than to deal with the failures later on. Some students may wonder what's the difference between reliability and quality. And it is important to understand the distinction between these two terms as they are often confused. Quality is the amount by which a product satisfies the user's requirements. It's largely a function of design and conformance to the design specification during the manufacturing process. Quality can help us answer that this product meets specifications when it leaves the factory. Reliability is concerned with how long the product continues to function once it becomes operational. Extend quality into time domain. Reliability can help us answer, will this product still meet specification after months or years of use? We can have a high quality product that is unreliable, or a low quality product that is very reliable. So a high quality product that's unreliable, I think about the car, the sports car. And for the low quality product that's very reliable, I will think about the hand tool sold in the Dollar Tree. They're not high quality, but because there's not a lot of moving parts, so it's still a tool, hand tool. Of course, the best products should have both the high quality and high reliability. Okay, let's walk through our example to illustrate how the reliability engineering works. So a company manufacturing small motors used in household appliances, and there are two issues they experience. One motor was abnormal high failure rate, and based on that observation, we can find out the possible causes of this failure, such as faulty design, defective material, or manufacturing tourism problem. And also, it is observed that the motor produced near the end of production run were failing at a higher rate than those at the start of the run. So we can point to the manufacturing process going out of control, which is a quality problem affecting reliability. And in our textbook, there's additional 2 examples to display how reliability engineering were applied in the real application. And please spare your time to read them. So reliability specification is very crucial, and we need to clearly define what constitutes failure and what function is performed. And we need to identify all failure modes and make the definitions unambiguous and observable. So try to avoid vagueness, such as reliable as possible, and but also be realistic. We cannot say that it will not fail under any operating conditions. And avoid using the mean time to failure or mean time between failure unless failure rate is constant. A good example of the reliability specification is like a 95% reliability at 10,000 operating hours. In this slide, we have the reliability specification example with the light bulb. It's 60 watts, an average lumen 870, an average lifetime 1,000 hours. So here we need to clearly define which average are we talking about. And are we talking about operation hours or the clock time? And how about the on and off cycles? And what are the operating conditions? So there's a lot of technical aspect when we define the reliability specifications. And we will cover those in our future chapters. There are several skills needed if you want to be a reliability engineer in the future. And the first one is the product system design knowledge. And you also need to understand the manufacturing and production processes. And life cycle cost analysis and management skills is also important. And you also need to know how to do the risk assessment and mitigation for the product and systems. And a typical path for a reliability engineer is finish undergraduate degree in the engineering field and have a couple of years of working experience, and then pursue a further study in the field of the quality with the reliability as the focus. And there are several certification offered. One of those is offered by the American Society for Quality, and they are highly desirable. And besides the ASQ, we also have the Society of the Reliability Engineer and Institute of Electrical and Electronic Engineer Reliability Society. So those are the information if you want to pursue reliability as your profession. In this textbook, we have a humorous but a telling perspective on reliability engineers. This highlights important truths. Reliability often brings unwelcoming news about the potential problems. But reliability engineers are the unsung hero to prevent many disasters. Every time we flip a switch, and it works. And every time you start your car, and it works. And every time we fly, and it can take us to the destination. Those are all the examples of the reliability engineering at work. So reliability actually is a very important field in the engineering field. And we are going to explore in the formal mathematical way and statistical way to learn about this deeper about this topic. And thank you for your time, and hope you guys enjoyed this topic, and let's continue learn about this. Thank you.